Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some topical questions on paper 1 for the topic of particle physics for Cambridge A-level physics. Now, as always, these questions are from the Papa Cambridge set of topical questions, and I'll leave a link to the Papa Cambridge website in the description below. And you can use these questions as a topical guide when you're studying for your paper 1 physics papers, topic by topic. And so this is the last topic in AS physics, or year 1 of the 2 years of A-level physics. And today we're going to be dealing with questions 1309 to 1322. And particle physics is not the most complex topic. There's very little in terms of mathematics, but the ideas for most of you, if not all of you, are going to be novel. There's going to be terms and quantities that you've not heard before. And so it's going to require something extra, some more effort on your part to make sure you understand the different concepts that are brand new. So the first question is 1309. It comes from the March 2020 exam. It's question paper 1, variant 2, and it's question 38 from that paper. We're told that two alpha particles with the same kinetic energy are moving towards and are then deflected by a gold nucleus. And we want to know which diagram could show the parts of the two alpha particles. Okay, so the thing I need to remember here is that this is the alpha particle scattering experiment. This is Rutherford's experiment, and this is an important one to know. And you need to know what happens, what the discoveries were, rather what the observations were, and what the observations tell us about the nucleus itself, and about, well, not just necessarily gold, but the nucleus of an atom. And I have two alpha particles. We can see that in the diagram they are slightly below the gold nucleus. But the gold nucleus is positively charged, and the alpha particles are also positively charged. We can assume that we already know this. And when the alpha particles move towards the gold nucleus, what we found was that those that were moving closer to the gold nucleus were deflected, but deflected to a greater amount than those that were moving further from the gold nucleus. So the ones that were slightly further, the alpha particles that were slightly further from the gold nucleus got a lesser deflection, and this happens because the electrostatic force, which you're only going to learn later on, what you do know is that the force is inversely proportional to the distance. So as you get closer, the force is greater. And as you get further away, the force is not as strong. So the alpha particles further away felt a smaller force than the ones closer to the nucleus of the gold atom. But the smaller distance means that there's a greater repulsive force, and specifically repulsive. So you cannot have the alpha particles being attracted to the positive gold nucleus, since the alpha particles are positive themselves. And so we're going to have to look for a diagram where the particles that are closer to the gold nucleus will get deflected away from the gold nucleus with a greater force than the ones that are further away. And we can see that corresponds to option D. So it's 1 repulsive, 2 it depends on distance. The closer you are, the stronger the force. And so that corresponds with option D. But again, these are things that you have done before, and you have read through the alpha particle scattering experiment many times. If you need a recap on that, then watch my crash course on the topic of particle physics, where I cover the alpha particle scattering experiment as well. Okay, the next question is 1310. That comes from the summer 2020 exam. That's May-June 2020. It's from question paper 1, variant 1, and it's question 39 from the paper. We're told that an element has two isotopic forms, and we want to know what the nuclear arrangements of these two isotopes are. So we basically need to recall what an isotope is. If you remember the definition of an isotope, then you've essentially just solved the problem, because you should be able to put together whether they have different nucleon numbers or different proton numbers, etc. But what is an isotope? An isotope are two elements, two variants of one element that have the same number of protons, the same proton number Z, but they have different numbers of neutrons. So carbon 12 and carbon 13, for example, they have the same number of protons, but different numbers of neutrons. And what this means is their mass numbers are different. They have a different nucleon number or mass number A. So Z is the same, but a different number of neutrons and a different number for the mass number or for the number of nucleons. So if I have my isotope, let's say my first isotope 1 has, so it's an element X, it has a proton number Z and a mass number A1 or a nucleon number A1. And then I have the second isotope of the same element X. We can use carbon as the example, but it could be anything. It could be uranium. And it has a mass number A2. It's different. So these isotopes will have the same proton number and different mass numbers. So this is how they would look. They would have the same symbol, C for carbon, U for uranium, etc. This number on the bottom would be the same, the number at the top would be different. So they have the same nucleon, or sorry, same proton number, but different nucleon numbers. And that corresponds with option B. Different nucleon numbers, but the same proton number. Because the number of neutrons are different, and the nucleon number is simply the number of protons and neutrons in the stable nucleus. Okay, the next question is from question 1311. It's from the summer 2020 exam. It's question paper 1 variant 2, and it's question 39 from that paper. We're told that an unstable nucleus goes through successive decays to become a final stable nucleus. The initial nucleus and final nucleus are isotopes of each other. How many alpha and beta particles could have been emitted during the decay sequence? Okay, a little bit of working to be done here. I mean, you could possibly just look at this question and then figure out what your answer is going to be. You can sort of use logic here. But I'm going to go with some mathematics because, as always, you know I like mathematics. So try to solve this problem mathematically. How many alpha beta particles could be emitted in this decay? So I have an unstable nucleus. I'll call this nucleus X, whatever this atom is. It has a number of protons Z and a nucleon number A1. It then becomes another atom, but it's an isotope of the original atom, so I'm still going to use the symbol X, with the same number of protons but a different nucleon number because it's an isotope. And I'm going to say there were n alpha particles. An alpha particle has a proton number of 2 and a nucleon number of 4 because there's 2 protons and 2 neutrons, giving 4 nucleons. And I'm going to say there were another integer m of beta particles, just using that to replace numbers. I don't know how many alpha and beta particles there were. And a beta particle has a proton number of -1, since its charge is -1, and it doesn't have any protons or neutrons, so the nuclear number is 0. So I want to balance the left and right hand sides, and I can see that if I balance the proton numbers, I get Z is equal to Z plus 2 plus 2n minus m. Now obviously the z's on either side would disappear, and what I'm left with is that 2n is equal to m. That means whatever the value of m is, however many beta particles are emitted, these are beta minus particles, however many beta minus particles are emitted, is twice as much as the number of alpha particles. And so if I look at the options I'm given, I could have n is equal to 1 and m is equal to 2, because that's the only option that will give me the number of alpha particles being half the number of beta particles emitted. So that means there's 1 alpha and 2 beta particles emitted, and that corresponds with option B. 1 alpha, 2 beta particles emitted. So when I see a question like this, I usually would write the balanced reaction equation out just so that I can mathematically solve for the number of alpha or beta, but you could see that you don't really need that. You could do this logically, you could do this step by step, but as I always say, it's always good to write things down very quickly, very briefly, very briskly, to make sure that you don't make any small errors which will give you a different answer. If it wasn't multiple choice, then you can argue that you would get marks for working, but since it is multiple choice, my suggestion would be to make sure. The next question is 1312. It's from the summer 2020 exam, question paper 1, variant 3, and it's question 39 from that paper. It says that radiation from a radioactive source has a range of a few millimeters in air and can be deflected by an electric field. Which type of radiation is being emitted? Okay, so technically we haven't really done electric fields yet, but basically the radioactive or the radiation being emitted will interact with other radiation, so it must be charged. Let's label all of our radiation and see if they fit the criteria. So alpha is charged, and that's fine. But they also say that it only has a range of a few millimeters. So the two important things that we need to realize here is that the range is small, it's only a few millimeters, and it must be charged. So those are two criteria. Alpha particles are charged, great. And they have a range of a few millimeters or a few centimeters in air. Okay, so that immediately agrees with our criteria. But what about beta minus? Let's do all and just make sure. So beta minus particles are charged. These are electrons. Remember, alpha particles are helium nuclei. They have 2 protons and no electrons, so they will have a charge of +2, so they are charged. Beta particles are just electrons, so they have a charge of -1. But beta particles can travel, and I'm just going to use a symbol, for an order of magnitude of a few meters in air. So this doesn't actually work out very well for us. Beta plus particles, which are just positrons, which are the antiparticles of electrons, are identical in almost every way. They also will travel a few meters in air, but that's not what the question says. The question says they will have a range of a few millimeters in air, so that can't be the correct one. And lastly, we have gamma. Gamma doesn't pass the first criteria for it to be charged because gamma particles are just electromagnetic radiation, so they're uncharged. And so all we are left with is option A for alpha radiation. Again, you could do this in a matter of 10 seconds because you already know which radioactive particle travels a short distance and is charged. That must be alpha radiation. But even though it travels a short distance, it's the most ionizing. So just be careful about that. The next question is 1313. It's from the March 2019 exam. It's question paper 1, variant 2, and it's question 39 from that paper. So we are told that a neutron is fired at a uranium-235 nucleus. The neutron is absorbed by the nucleus, which then splits to form nuclei of barium-141 and krypton-92. What is the number of neutrons emitted when this nucleus splits? Okay, so this is actually something called nuclear fission, which you're going to learn in A-level physics when you study the topic of nuclear physics. But if I just follow the instructions, or not the instructions, if I follow the ingredients that are given, I can write down what the recipe is. So I have uranium-235. I slap it with a neutron. After slapping the uranium-235 with the neutron, it doesn't like this very much. It then becomes agitated, becomes unstable, and then splits. And when splitting, it forms barium, which is also radioactive, but a lot more stable than uranium-236, which is formed when the neutron collides with uranium-235. We have barium-14156, and we have krypton-9236 plus some number of neutrons. And the neutron has 0 protons, obviously, and 1 nucleon, 1 neutron. And there's some numbers, that integer value, we'll call it b. I'll just use the lowercase letter b. And so I have to figure out what this lowercase letter b is. And let me balance the proton numbers and nucleon numbers on either side. If I balance first the nucleon numbers, well, that's going to be enough actually to get me to what I want. I have the left-hand side 235 plus 1 must equal to 141 plus 92 plus B, because there's just one neutron for, well, every neutron. And then I can simply solve for B, which again, most of you will probably do while sleeping, and that gives me B is equal to 3, which is option D. And so when I need to figure out how many neutrons are emitted or how many of a certain particle is emitted, I can either balance the mass number or the nucleon number like I did here, or maybe I need to balance the proton number for a different example. But either way, you'll be able to use this method to figure out what the missing number of whatever particle we're interested in is. Okay. The next question is 1314. It's from the March 2019 exam. It's from question paper 1, variant 2, and it's question 40 from that paper. We want to know which word equation represents beta plus decay. Okay, which word equation represents beta plus decay? Well, what is beta plus decay? Well, we can do beta plus decay mathematically, but in beta plus decay, we have a proton. Remember, it's this weak interaction weirdness that happens where a proton becomes a neutron and a positron is emitted in the process, which is your beta plus particle, and an electron neutrino, not an antineutrino, but a neutrino. A neutrino is a tiny particle. It doesn't have any protons or neutrons, so its proton number and nucleon number are both 0. And some energy is also usually given off in this process. So proton becomes neutron plus positron. A beta plus particle is a positron. It's the antiparticle of an electron plus an electron neutrino. If it was beta minus decay, we'd have an electron antineutrino. And so this corresponds with option D. Proton becomes neutron plus positron plus electron neutrino. Okay. So that was, that again, by definition, we need to know what beta plus decay is, what beta minus decay is. And unfortunately, like I said at the beginning of this video, these are quite novel things. These are not things that you would have seen before unless you were just really interested in studying, well, nuclear physics or particle physics on your own terms, because it's not something that you would cover in high school. So the next question is question 1315. It's from the summer 2019 exam. It's question paper 1, variant 1, and it's question 39 from that paper. So this question says, which statement about the alpha particle scattering experiment provides evidence for the existence of the nucleus? A tiny proportion of the alpha particles are deflected through larger angles. Slower alpha particles are deflected through larger angles. The kinetic energies of the deflected alpha particles are unchanged, and the number of alpha particles deflected depends on the thickness of the foil. Again, it's one of those questions where if you read through the alpha particle scattering experiment, then you probably don't need to read through the options. You'll select the correct option. But essentially in this experiment, we had we have an atom, and we want to determine if the atom actually has a nucleus, has collections of positive charges or a single positive charge. And what we do is we fire these alpha particles through the atom, which we know are positively charged, to see what happens. And what we find is that those that are further away are slightly, ever so slightly deflected. And those that are closer to the nucleus are deflected to a greater degree. And then a very, very, very small fraction, tiny fraction, that are sent almost directly towards a head-on collision with the nucleus are actually deflected through large angles, some of them almost 180 degrees. And then on the other side, the same thing would happen. The deflection depends on distance. Now, what does this actually show? That shows that, firstly, so many of the particles, I didn't show them here, but many of the alpha particles were undeviated. They were too far from the nucleus for anything to actually happen. But a very small percentage were deflected by large amounts. So some large angle theta. And because this was only a very small amount, what this told us was, and again, they were pushed away from the nucleus, not pulled towards the nucleus, then we figured that the center of an atom is, or the nucleus of the atom is positive, and it's quite small. If it were bigger, there'd be a larger percentage of alpha particles being deflected by these larger angles. The nucleus is small and the nucleus is positive. And this corresponds with option A. Tiny proportion of the alpha particles are deflected through large angles. That's the observation that tells us that the nucleus exists. Okay, the next question is 1316. It is from the summer 2019 exam, from question paper 1, variant 2, and it's question 38 from that paper. We are told that a nucleus of francium-221 decays into a nucleus of bismuth-209 in several steps, and we want to know which particles could be emitted in that process. Could we have 2 alpha particles and 4 beta minus, 2 alpha and 4 beta plus, 3 alpha and 2 beta minus, or 3 alpha and 2 beta plus? So how are we going to figure this out? Well, basically, I'm going to write down, like I've done before, I'm going to write down the reaction equation. So I have francium, Fr, 221 and 87, which is unstable and decays into bismuth, Bi 209 and 83. And I know there's going to be alpha and beta particles emitted because those are contained in all of the options. So this might be a little bit messy, but I have n number of alpha particles, alpha being 2, 4, plus another integer value m of beta minus particles that are electrons, minus 1 and 0, plus some other integer value k of beta plus particles. That's beta plus 1, 0. And all of these values here are positive integer values. So n, m, and k are all positive integer values. So now let's balance the nucleon numbers first. So let's balance the A's, the numbers at the top. And what we have is 221 is equal to 209 plus 4n, because there are no nuclear numbers for the positron and the electron. And so immediately I can see that n is equal to 3. Okay, so that tells me immediately I have 3 alpha particles. So I can eliminate options A and B. It must be option C or D. But let's figure out whether it's going to be beta plus or beta minus particles. Again, you could do this just by looking at the problem without actually writing down the maths. But balancing the proton numbers, I have 87 is equal to 83 plus 6, because I already know that there's 3 alpha particles, plus m times minus 1, or I can simply say minus m, plus k times 1. Okay, that's the proton number for a positron and for an electron. And we did say that n, m, and k are all positive integer values. Okay, so we have 87 is equal to 89 Now 89 minus 2 is going to give me a number. It can't be, we have to get rid of k. K must be 0 because I can't take a number bigger than 87 and then add it to another positive number to get a number like 87, to get a lower number. So I must have that this is 89 minus m. And so m is equal to 2, which means we have 2 electrons, 2 beta minus particles, because the proton number on the left-hand side is smaller than the proton number on the right-hand side. So we had to subtract 2 electrons in order to balance the proton number. And so this corresponds with option C, 3 alpha particles and 2 beta minus particles. Again, a lot of working, much of which you probably a lot better at solving in your head than I am. So by all means, if you can solve these problems with much quicker methods, then do so. But this is the method that you would solve it if you were solving it in a paper 2 question, for example, if you were doing it step by step. The next question is 1317. It's on the summer 2019 exam. It's question paper 1, variant 3, and question 39 from that paper. We are asked the correct estimate of the order of magnitude of the diameter of a typical atomic nucleus. Now, to be quite honest, this is something that you're probably just going to have to remember. But how I remember this is, and this may seem also like an abstract thing to remember, but again, I'm a physics teacher, so there's some things which I'm doomed to remember and never forget. And things like the range of the strong force. The strong force only acts when objects that contain quarks, your proton and neutron, for example, come within a range of 10 to the minus 15 meters. In fact, the range of the strong force is anything below 10 to the minus 15 meters. That's a very tiny range. So obviously, what this means is that the diameter of an atom must be anything greater than the range of the strong force. The diameter of an atom can't be smaller than the range of the strong force, because then the strong force would be acting outside the atom as well. But we know this doesn't happen. It only acts within the atom. And the only number in the options there that is greater than the range of the strong force is 10 to the minus 14 meters. So 10 to the minus 14 meters is greater than 10 to the minus 15 meters. And so the diameter of an atomic nucleus typically is 10 to the minus 14 meters. Again, like I say, this is a very abstract way of remembering it, but whatever works for you. Sometimes good old memorization is important, and it's as important in physics as it would be in any other subject. The next question is 1318. It's from the winter 2019 exam. That's October, November 2019. It's question paper 1, variant 1, and it's question 39 from that paper. We are told that an unstable nucleus of an element decays by emitting an alpha particle or a beta minus particle to become a nucleus of a different element. This nucleus is also unstable and also emits an alpha particle or a beta minus particle. The process continues until an isotope of the original element is produced. What is the minimum possible number of these particles that can be emitted? The minimum number of particles. Okay, this is kind of a tricky one. Not kind of a tricky one, it is a tricky one. Now, what I know is that there is an element X. It has a proton number Z, a neutron number A. Actually, we'll call it A1. And then it decays to become another element Y. Actually, it becomes the same element because it's an isotope. So same element X, proton number remains the same, but the nucleon number becomes A2. That's the only thing that changes for an isotope, plus an integer value of alpha particles plus another integer value of beta minus particles. Okay, and remember an isotope, same Z, different A's. So what are the proton numbers on both sides of this reaction equation. So I have Z on the left-hand side, and this is equal to Z plus 2n minus m. And so what I get here is that 2n is equal to m, like we've seen in the previous question already. So if n is equal to 1, what this means is that m is equal to 2. So I've taken the lowest possible number of alpha particles that are allowed to be emitted, which is 1, and that gives me 2 beta particles that are emitted. And so the minimum number is n plus m, and in total there are 3 particles emitted, 1 alpha, 2 beta. So the minimum number of particles is actually b. So we've actually done a similar question early on, but with the actual numbers. But for a problem like this, you usually see that, well, the minimum number will be 1 alpha and 2 betas. And that will allow the reaction equation to balance on either side. And if I had 2 alphas, then I would have 4 betas and so on. But that would not be the minimum number of possible particles emitted. Okay, so that was option B. 3 particles at least will be emitted in that reaction. Now the next question is 1319. It's from the winter 2019 exam, question paper 1 variant 2, and it's question 38 from that paper. Okay, so this one was quite interesting. Well, depends how you define interesting. If you're a physics student, you probably would want fewer interesting questions right about now, just before your exam. But nonetheless, we enjoy a challenge. Hopefully we enjoy a challenge. And we are given a table with some data relating to 4 neutral atoms, W, X, Y, and Z. We have the nucleon number and the total number of particles in this neutral atom. That is, protons, neutrons, and electrons. 2 of the atoms are isotopes of the same element, and we want to find the proton number of this element. Remember, isotopes have the same proton number, but different nucleon numbers. Wow, okay. So, by definition, mass number, or nucleon number, is number of protons plus number of neutrons. I'm going to call it P plus N, and I'm going to label this equation 1. The total number of particles, which is the second line, second row in this table, I'm going to label it T. And this is protons plus neutrons plus electrons. We rarely ever add all of these 3 things together, but we're doing so in this table. But wait a minute, this I can write as 2p plus n. And I can just throw the e away as if it's not important to us. And I write this equation as number 2. Now, why do I do this? That's because for a neutral atom, the number of protons is equal to the number of electrons. And that's because the charge on a proton is positive 1 and the charge of an electron is minus 1. So I need to have the same number of protons as I do electrons in order for the atom to be neutral, have no charge. So I can say P is equal to E, and simply T becomes P plus N plus P, which is 2P plus N. Okay, where am I going with this? Let me subtract these 2 equations, 2 minus 1. What I get is the total number minus the mass number is obviously going to give me the number of protons. Now for isotopes, for any 2 atoms, I have to still figure out which of these 4 atoms, which 2 of these 4 atoms are isotopes of each other. For isotopes, we need that the proton numbers must be equal. P1 and P2 must be the same. This means, from the equations I derived above, that the total number minus the nucleon number must be equal for those 2 atoms. So T minus A must be equal. And in which case am I getting equal numbers when I subtract the bigger number, the smaller number from the bigger number? Well, 24 minus 16 is 8, 26 minus 17 is 9, 25 minus 17 is 8, and 28 minus 18 is 10. So that's W and Y. have the same number of protons. So those are the two isotopes. Hooray! So now I've determined that I'm only really concerned about W and Y. So I'm concerned about W and Y. But I want to find the number of protons, because for the isotope, they will have the same number of protons. But wait a minute, proton number, I can use my equation that I derived above, is T minus A. So for either one of these, it's the bigger number minus the smaller number. It's 24 minus 16, or it's 25 minus 17, which is 8. And that corresponds to option B. So again, by process of elimination, by deduction, you can solve this problem, but mathematically, the mathematics will not fail you, and doing it correctly will give you the proton number of this element being 8. Okay, a little bit more out of the box kind of question. And the next question is 1320. It's from the winter 2019 exam. It's question paper 1, variant 2, and it's question 39 from the paper. Now we're given a selection of particles and we're asked to say which one is not fundamental. Okay, so we're asked to discriminate against these particles, and unfortunately we're going to say one of them is not a fundamental particle. So the others are fundamental, but one is a standout. So we have to figure out what's different for each of these particles. So if I say, well, here's the electron. Does an electron have quarks? No, it doesn't. There's no quarks in an electron. So it is a fundamental particle. Any particle that is made of quarks, or consists of quarks rather, is not a fundamental particle. What about a neutrino? Neutrinos are tiny. They are also not composed of quarks. And they will not respond to the strong force. They are not a fundamental particle. What about a neutron? Well, what we know is that the neutron lives in the nucleus. Anything that lives in the nucleus is not a fundamental particle because it will be made of quarks. So if it's either a neutron or a proton, it does have quarks. And so it's not fundamental. Fundamental meaning cannot be broken down any further. But let's just test the last option, D, which is the positron, which is just the antiparticle of the electron. Also has no quarks. It's not the same particle as an electron, has mostly similarities and a few differences here and there, but also is a fundamental particle. So the only particle that is not fundamental from that list, as again would take you probably 30 seconds to answer, the correct option there would be option C. The neutron is not a fundamental particle. The next question is 1321. It's from the winter 2019 exam. It's from question paper 1, variant 3, and it's question 39 from that paper. We're told that a radioactive nucleus emits an alpha particle or a beta minus particle, creating a product nucleus, and we want to know which decay could create the product nucleus stated. So we've done so much of this already. What does alpha decay tell us? Well, alpha decay happens when an atom X with proton number Z and nucleon number A becomes another nucleus Y, where its proton number is reduced by 2 and its mass number is reduced by 4, and we have an alpha particle to fill in those gaps, 2, 4. What is beta decay? Well, beta decay is when a nucleus X, proton number Z and mass number A, decays to form another nucleus Y with a different proton number but the same mass number, plus beta minus 1, 0. So the mass numbers and proton numbers balance on either side of the arrow for both alpha and beta decay. And we can also add some energy in as well. And so I have to look at each row of this table and figure out which row actually fits. Well, if I take radium 226 undergoing alpha decay, if I subtract 4 from 226, I do not get 224. So immediately I can eliminate option A. What about option B? Uranium 238 alpha decay. Well, if I subtract 4 from 238, I definitely don't get 242. So it can't be plutonium. What about radium 228 rather? Undergoing beta decay to become francium 228. Well, we have the proton number decreasing by 1. It should increase by 1, so it can't be option C. And so we're left with option D. Thorium 23190 undergoes beta decay. Its mass number remains the same, 231, and its proton number increases by 1. So that looks like our perfect candidate. 231, I'll write it down so you can see. 231 and 90 becomes protactinium. Protactinium 231 91. So PA is actually protactinium, also radioactive, and that corresponds with option D. Okay, so that one is a little bit more okay because we're actually given the nuclei, the daughter nuclei and the radioactive nucleus. So we were told what the nuclei were, and we could just do the mathematics quickly to check which would be the correct answer. So we didn't have to do any fancy calculations there. Now the last question for this video that we'll do is 1322 from the March 2018 exam. It's question paper 1 variant 2, and it's question 39 from that paper. So this one can be a little bit tricky. This question can easily make you choose an option that you may think is correct but is not actually correct. But as always, I'm going to use a method that is very sort of mathematical in nature because that's just the way my brain works. But again, it obviously is up to you what you feel comfortable, how you feel comfortable going about solving this problem. A nucleus of neptunium-236 contains 93 protons and 143 neutrons. This nucleus decays with the emission of an alpha particle. The nucleus formed then emits a beta minus particle, which diagram shows the changes in the number of protons and the number of neutrons in these nuclei. So first I have a nucleus, then happens alpha particle, then neutron number and proton number change. Then happens beta minus decay, and I'm given a new proton number and new neutron number. And I'm basically plotting a graph of proton number against neutron number. Proton number on the horizontal axis and neutron number on the vertical axis. So what's my first state? My first state is neptunium 236 and 93. What do I have? I have a proton number. I'm going to use P because I'm matching what they have in the question. Proton number P is 93. Mass number A is 236. Neutron number is A minus P, total number of nucleons minus the number of protons, which leaves us with the neutrons, which in this case is going to be 143. This means that my point Pn, my coordinate is 143 and 93. But what you'll find is that corresponds to all of the graphs. The starting point is all 143, 93. Okay, that's fine. Let's see where the next part takes us. Now we have this neptunium 93, 236 that is undergoing alpha decay. So it becomes some other nucleus. Doesn't really matter what it is for now. 91, 232 plus my alpha particle 24. So I made sure my equation on either side is balanced. 91 plus 2 is 93, and 232 plus 4 is 236. So it's one alpha particle. The number of protons of my new nucleus is 91. The mass number of my new nucleus, my daughter nucleus, is 232. And so the neutron number is 232 minus 91, which is 141. This means that my new point on my coordinate system Pn is going to be It's going to be 91 and 141. And actually, my previous one should be 93 and 143. I switched around the coordinates here. 93 and 143. P is the first coordinates, the horizontal one, which we always sort of by convention label first. Now I have 91 and 141. So immediately I can see that this is here, 91 and 141, 91 and 141, 91 and 141, and 91 and 141. So I can already eliminate options A and C, and I'm left with options A, or rather B and D, which are following the pattern of the graphs. So I just need to do the final beta decay to determine my final answer. So then I have finally this unknown element, unknown nucleus X with 91 protons and 232 nucleons, decaying and becoming another nucleus Y with 92 protons and 232 nucleons, plus a beta minus particle, an electron. So my new nucleus in this case, P, has a proton number P of 92, a nucleon number which is unchanged from the last nucleus 232, and a neutron number which is 232 minus 92, which is 140, which means my new coordinate would be 92 and 140. My final coordinate, 92 and 140, which would be there, 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 aha, and there. So the only graph that matches all of our proton and neutron numbers is option D. Option B deviates at the last beta interaction, but graph D matches all of our proton and neutron numbers. So in this case, I had to write down each one of the decays that are happening and then make sure that the numbers on the graphs match those decays. Do you need to do all this writing? Once again, I'm going to say no, you don't need to, but if it helps you, then do so. But make sure you're doing it efficiently because you don't want to spend too much time. But this is the thought process that you would have when solving these problems. I'm not a big fan of solving these problems quickly, rushing through them and showing you tricks. I would rather show you how the problems would be solved, and then you can figure out the tricks that work in order to save you time. So I hope these questions were helpful for particle physics. You can see that particle physics is a novel topic. It's something new. It does require reading and rereading and background reading if possible. But with time, you realize there's not that many concepts. There's only a finite number of concepts that you need to know for A-level physics, at least. And I hope this video was useful. If it was, please leave a like, leave a comment down below if there's anything you want to say. Subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.